All right, let's take a look at this particular problem, which involves double shear and single shear. Okay, so what we have here at the top is we have this bar that goes across. We have 3,000 pounds being pushed out 4 feet from A, and then we have this rod BC that's being pinned. Okay, so there's a pin at A and then there's a pin at B, and we can calculate what the shear stress is in both. Okay, however, pin A, if you notice, there's two sides pulling on that pin back to the left. Okay, so that's called double shear. On this side, you have one being pulled to the left and you have one being pulled to the right. That's single shear. Okay, if you wanted to add double shear on pin B, you would have to have another one of these on that side. So it would be like right here. Okay, so let's go through this problem. Let's pick DA to be 7/16 inch, the pin at B to be 5/8, and let's pick a safety factor of 2, and we're going to go with, we're going to find, so this is given, we're going to find what? Tau A, tau B, so shear stress in the pins, tau B, and then we're going to find the diameter of the rod of a safety factor of 2. Okay, so let's go over here. Let's do a sketch. I'm going to do our free body diagram, and I'm just going to do just like a line. So here is basically a Y, a X. Over here is your 3,000 pounds. And then we have FBC, the rod. This is FBCY and FBCX. Now, over here, let's do it in green. This is theta. So cosine of theta is 4/5, and sine of theta is 3/5. Cool. All right, let's get right to the solution. So solution starts below everything. Let's find FBC. So in order to do that, we're going to take the moment at A and set it equal to 0. And we're going to assume counterclockwise is positive. So we get negative 3,000 pounds times 4 feet. Okay, plus FBCY times 6 feet. We set that equal to 0. All right, we're taking the moment at A, so those two forces go away, and then FBCX goes away because that's in the line of action. Okay? What I'm going to do next, negative 3,000 times 4 plus FBC. Y would be sine, so it's really 3/5 times 6 equals 0. So we can actually solve for FBC, which is 3,333 pounds. All right. Now, let's go ahead and find a X and a Y, and we're going to sum the forces in the X, set it to 0. To the right is positive. Sum the forces in the Y, set that equal to 0, assume up is positive. So we have AX plus FBCX equals 0. AX plus FBC of 4 divided by 5 equals 0. Over here we have AY minus 3,000 plus FBCY equals 0. AY minus 3,000 plus 3,333 times 3/5, right? Because that's the Y. And let me plug it in here. 3,333 times 4/5 equals 0. So AX becomes 2,667 pounds, and AY becomes 1,000 pounds. All right. Now let's find A. A equals square root of AX squared plus AY squared. A equals square root of 2,667 squared plus 1,000 squared. And you get A to be 2,848 pounds. Okay, so we've now found AX, AY, FBC, and now we can go ahead and do our shear calculations and then our sigma calculations. Okay, so let's take a look over here because they've kind of split it up nice. So if you look here at pin A, you have 2,850 rounding up acting this way. Okay, and then because you have to use the magnitude, because that's what the shear force of the pin experiences, you divide these by 2 because there's 2 sections where this could shear. Okay, because there's this section and then this section. Okay, so you split this magnitude of A up into 2 parts. So you get 1.42 going backwards. So that's the force that you're going to use, the shear force, when you find tau. Now over here at pin B, we have only 1 on both sides. So you're going to use, again, the magnitude, but you don't need, there's nothing that splits it up because it's not double shear. It's only single shear, meaning there's only 1 on this side being pulled left and then this side being pulled right. Okay. So let's go ahead and calculate those. So let's find tau A. Tau A equals the shear at A over the area at A. And we got to use that magnitude divided by 2. And it's pi over 4 d squared, which is 7/16 inch squared. So tau A becomes 9.5 kip per inch squared. Sorry. All right, let's box that. Let's find tau B. Tau B equals VB over AB, and this you use the magnitude over pi over 4 times 5/8 inch squared, and tau B, because it's single shear, 10.8 kip per inch squared. Okay, so double shear for A, single shear for B, and then we found those, and the last thing we can find is the diameter of the rod. Sigma equals P over A. We're going to look for A, which is P over sigma. We're going to use a safety factor of 2, so we're going to multiply that force by 2. So 2 times 3,333 pounds over 11.4 KSI, because we're going to be using, I didn't put that, did I put that in the givens? No, let's put that in the givens. Sigma that we're going to use, I believe it is copper, red brass. It's got a yield sigma of 11.4 KSI. So that's the pin that or the rod that we're using. Okay, we want to make sure that we have a big enough rod. And we're just going to multiply that by 1,000 to get it into PSI. So the area becomes 0.585 inch square. And now we can solve for the diameter because it's d squared over 4. The diameter is square root of 4 times A over pi. Square root of 4 times 0.585 inch squared divided by pi. The diameter becomes 0.863 inches, or you can get it 7/8 inch at the store. Okay. So again, in summary, we looked at this problem. We had a pin at A, we had a pin at B. We wanted to find the shear stress. Okay. And what you could do is you could actually use the shear stress, tensile stress, go back to the book, find out what type of material that you could use for this so it would hold up. Okay. So we found tau with double shear for A because there's two things acting, being pulled back. At pin B, it's only single shear because there's only one on one side. We had to basically sum the moments, sum the forces to find the reactions, and then do free body diagrams on the pin to find the shear forces, find the shear forces, and then we ended up finding the diameter of this rod, right? Because we know the force, and we know we're trying to use copper. I believe it's, what do they say? Copper, red, brass. It had a sigma y of 11.4 KSI. And we found that diameter we should be using is 7/8. Okay, I hope this helps, and good review. Take care. Thank you.